In this video, we're looking at gates. If you look at pages 92 and 93, you will see we are now in the hardware layer. So we've moved from the information layer, learning how data is represented inside the computer, and we'll be looking at the actual gates and transistors that's making the computer move these ones and zeros around. As you see on page 93, what we're concerned with in this chapter is the control, the flow of electricity. Moving on to page 94, let's get a few definitions out of the way. First, what is a gate? So a gate is a device. It's going to perform the basic operations of electrical signals. You will see in section 4.2 on page 96 that this chapter is looking at 6 different types of gates. Now, programmers are going to primarily be concerned with the NOT, AND, and OR gates. I use these operations all the time when I'm programming. Exclusive OR, NAND, and NOR gates are used more on the technology side in making the circuitry. Okay, let's look again at gates. Gates will accept one or more input signals and produces exactly one output signal. You combine gates to create circuits. You will see that you can have both combinatorial and sequential circuits. So a circuit is a combination of gates that perform a specific logic function. And so, for example, there is a circuit that does adding of binary. It adds the 0 and 0 and the 0 and 1. There are 3 different notational methods for gates, and we will need to learn all 3 of them. One is Boolean expressions, and one is logic diagrams, and one is truth tables. So as we're going through all of the gates that was in section 4.2, we will learn the Boolean expression, logic diagram, and truth table for all 3 of these. Now let's move down to consider what Boolean algebra is. So a Boolean expression is a form of Boolean algebra. Boolean algebra was created by George Boole. Now, George Boole was a mathematician and he created logic. And this logic was all theory in the 1800s. And once again, the theory proved to be applicable to computers, and so the logic that George Boole created, we honor him by naming the operators of this logic Boolean operators. So let's take a look at the first gate. This is a very simple gate, the NOT gate, and there are 3 different notational ways to indicate this, and here's Boolean, here's the logic diagram, and here's the truth table. So the NOT gate is going to take one input, and that is A, and produce one output, and that is X. This Boolean expression here is known as an assignment statement. Now, an assignment statement is a very important concept in computer programming. You will be using it all of the time. Let's take a closer look at it. Now in school math, you remember doing something like this, 3 plus 4 equals X. And in school math, you always put the answer over here on the right-hand side. Well, maybe always, until you got to algebra and you did f of x. So the answer went on the right-hand side. However, with programming, we do the opposite. So in programming, you might be doing something more like this. X is the answer. And notice it's on the left-hand side of this operator. Okay? And this is the expression. And in programming, X, A, and B are all called variables. Now, variables should contain data if they're on the right side. Over here in RAM, we will now have some data, and we'll have the variable A pointing to a location in RAM. Now, so this is a byte, let's say, and let's say this contains the value 5. Of course, it's stored in binary. And let's say B is being pointed at RAM, and let's say it contains the value 6. And so when this expression is evaluated, what's going to happen is the value A will grab 5, and the variable B will grab the value 6, and the expression's completed, making 11. So that 11 then gets stored in RAM, being pointed to by the variable X. Okay, so that is what an assignment statement is, and so we'll call this the assignment operator. So just as this is an operator, this is the mathematical operator, this too is an operator, this is the assignment operator. Let's review again. A NOT gate is going to accept one input signal, and of course this is electricity. We're going to associate the binary values 0 and 1. But in logic, or in programming, we'll think of 0 as meaning false and 1 as meaning true, and returns the complementary opposite signal as output. So do you remember doing 2's complement? Do you remember in step 2, you flip the bits, 0's become 1's and 1's become 0's? This is the gate that is responsible for flipping those bits. Okay, now one more time, let's look at these notations for the NOT gate. So we have the assignment statement, X is assigned the value of not A. If A is true, X is false. Or if you want to use 1's and 0's, if A is 0, X is 1. If A is 1, X is 0. This is what our author decided to use for the NOT operation, and as you're reading through the textbook, you'll have to understand that this symbol here means not. Take whatever A is and make it the opposite. However, in programming, there are many symbols associated with that operation. So let's take a look at a few of them. Here I am at Wikipedia, and Wikipedia is going through Boolean algebra. And right here, let's see, I have the NOT operation, and the operator, as you can see, is this little symbol there. Sometimes you might see it as not X, NX, or even an exclamation mark X. So that are different symbols, all mean not X, and our author uses that little hash right after the operand. Here I am with C#, and Java also uses this. And so this operator right here, that is our NOT operation. So what this is saying is 1 equal to 0. Are they the same? Well, that's false. 1 does not equal 0. So inside the parentheses, we have a false statement. However, we're noting false. So not false is true. So this entire expression is true. Result will be assigned the value of true. But the point is, if you don't understand that, that's the NOT operator there. And finally, here I am in Visual Basic, and you will see in Visual Basic, we simply use the word not for our NOT operator. Now, NOT is a unary operation. Okay, you notice that it only operates on the one operand. Okay, and that's why we got only one input. So now let's take a look at the logic diagram. So the logic diagram, we've got this triangle followed by this circle. We're going to call that circle the inverter. So it inverts the input. Okay, the inverter is flipping the bits. Finally, we will do the set of all possible inputs and see what the output will be. So this column A is representing the input, and this column X is representing the output. When 0 is input, the output is 1. When 1 is input, the output is 0. That's all A can be, 0 and 1. Or likewise, you could write true or false. So this could be true. If A is true, not A is false. If A is false, not A, which is X, is true. Now let's consider the AND gate. Now the AND gate, you notice, takes 2 input signals. So in fact, the remainder of the gates will take 2. Not is the exception. So you will notice that we have 2 operands here in the Boolean expression. We have A and B, inputs A and B, and in the truth table, okay, we now have 2 columns representing our input and 1 column X representing our output. And we will always end up with 1 column representing our output. This is read X is assigned the value of A and B. Now, in some languages, we'll use 2 ampersands for A. Java, C Sharp, we'll use 2 ampersands. I've seen that symbol used for and you might just see me write the word and out, meaning A and B. Okay, in the logic diagram, we just have this symbol here. Let's just think out loud about and. So I say to my grandson Rico, I say, Rico, you can go outside and play if you've made your bed and you have done your homework. So let's say he's done neither of these. Well, if he's done neither of these, then A and B are false. And let's say X represents the result. In this case, the result is he can go outside and play. So if he has done neither one of them, the result is no, you can't go outside and play. Let's say A means he's made his bed, B means he's done his homework. In this case, he has not made his bed. He has done his homework. He still can't go out to play. And let's say here, oh, he's made his bed, but he has not done his homework. He still can't go out to play. Finally here, we have the fact that he's done both. And with and, both inputs must be true. When both inputs are true, the result is true. And so we've used and forever, right? We've always been using and so when you do a Google search, you know you've been doing and you've been using the term and in your speech, and it works similar in logic. Okay, here is the OR gate. Now the OR gate will also accept 2 inputs, give us a single output. Now if both of the inputs are 0, then the output is 0, otherwise the output is 1. So let's go to the truth table first. Now once again, we've got 2 inputs and 1 output. But let me go back to Rico, and I'm going to say to him, now I'm going to replace this operator with OR. Now Rico, you can go outside to play if you've made your bed or you've put away your toys. Now, that or implies he doesn't have to do both. So in this case, he hasn't done either. He's neither made his bed or put his toys away. He's not going outside. Well, now let's say, yeah, he hasn't made his bed, but he's put his toys away, so I'm going to let him go out. Or he's made his bed, hasn't put his toys away, he can go out. Or he's done both. He's been a very good boy, so he's going to be able to go out. Notice with the and, let's go back up to the and. Notice with the and, you only get a 1 when both are true. So it's only true when both of them are true. Notice with the or, it's only false when both of them are false. Okay, so here is our Boolean expression. This is read as X is assigned a value of A or B. So I think that plus sign's a little confusing. I'd rather have you use the word or in Java and C Sharp. They will use these 2 pipe characters. The pipe on my keyboard is right below the backspace key. Okay, so A or B. And here is our symbol, kind of looks like an arrow, and this is the symbol for or. So let's just transpose this. Suppose A is 0, B is 1. These are our inputs. What's the output for X going to be? Well, 0 or 1 is 1. Those first 3 gates are the most common gates that are used in programming. Now, as far as creating circuits, there's also the exclusive OR gate. I may have used it in programming before. I cannot remember. I haven't used it frequently if I have used it. Well, the exclusive OR gate, so XOR is how I'll pronounce it. It takes 2 input signals. If both of them are the same, if they're both the same, the output is 0. Otherwise, the output is 1. So here is our symbol our author is using for XOR, and I'll probably just write XOR whenever I want to refer to XOR. Okay, X is assigned a value of A, XOR, or exclusive OR B. Looks like an OR symbol in the logic diagram, just got this extra arc here. Okay, now you'll notice in the truth table, again, we got 2 input columns, 1 output column. Notice when they're the same. Here, both inputs are the same. So both inputs are false, the output's false. Here, both inputs are true, the output's false. But notice here, we got a true input, or got a false input and a true input, the output's true. We got a true input and a false input. The output's true. And you will see we'll be using exclusive OR when we start doing the adders. So it is a good gate to know for circuitry. Now we have the NAND gate. And the NAND gate is actually two operations. See, here I have the AND operation, and I'm knotting it. So here's the AND operation. We do that first because it's inside parentheses. And then we're going to knot the result. So if A were 1 and B were 1, well, A and B is 1, but then we'll knot that result, and X will be 0. Notice in the logic diagram, it looks like an AND symbol with that little circle inverter. So it takes, just do a logical AND, then flip it. That's what you're going to do. Okay, so 0 and 0 is 0. But then we're going to knot it. So a NAND gate will knot that result and we get a 1. A 0 and 1 is 0. Knot it. That's what not and is. NAND is not and. So a 0 becomes a 1. A 1 and 0 is 0. We knot it. It's a 1. A 1 and 1. Oh, that's 1. But we knot it, and that's a 0. Well, okay, we're down to our last gate, and that's a NOR gate. Again, the NOR gate means not or. Okay? So notice that it's the opposite of the OR gate. Again, when we have 0 or 0, we get 0, but we're going to knot it, get 1. For all the rest of these with the OR, all these end up being 1, but when we knot it, we get 0 as the result. Notice it's two operations. It's the OR operations, and then we take that result and we knot it. And again, the symbol is the OR symbol followed by the inverter. So those are our gates, and those are the notations that we will be learning, and you'll be working in combining these gates and seeing how they make circuits in the next video.